So let's give you a quick introduction to multiple linear regression. This is our usual regression setup with the features, the label, and the predicted label, f of x. Now I'm going to propose a very simple function that takes into account all the various factors and weights each of them by some amount. Okay? So this model is linear, meaning it's just a weighted combination of the factors. But in reality, the model could be very complex. For instance, you could multiply some of the features together and use those as a new feature if you wanted to. In any case, where am I going to get these weights in reality? Right? I could make them up, but that's not really a good idea because it ignores all the data. So let's learn them instead. So I'm going to stick to linear models like this for now. So the b's are just these coefficients, which are 3, 10, 100, whatever in the example. So we'll take our linear model, and then the method of least squares is simply to choose the coefficients, the b's, to minimize the sum of squares error. Okay? So the weights are learned from data. Right? How do we do this? Right? This is an optimization problem that's exactly the same as the one for simple linear regression. The only difference is the function can take has multiple terms in it. And this is called the method of least squares. Once again, you don't need to program this yourself. In fact, actually, solving this problem is particularly easy for a computer since there's an analytical solution to the minimization problem for this case. So all you need to do is give it the data and tell it to do least squares regression, and boom, you're done. You have the b's, and you can use them in your predictive model F. You can be creative in the choice of features you're going to use. Like I said, you can use polynomials, you can square the variables, cube the variables, you can multiply them together. You could create indicator variables. Like this variable is 1 if the age of the person is above 60 and 0 otherwise. If you put too many variables in there, the optimization problem gets harder, and you could run into cursive dimensionality issues. But you really should put what you think are all the potentially important factors in there. If you did put polynomials in there, it would allow the function to be kind of curvy and interesting, sort of like that with all the curves. Although you can see already that if you put too many interesting features in there, you do run the risk of overfitting. So we're going to have to handle that a few lectures from now. But you really should put in all the main features that you think are likely to be predictive.